Why do linked lists still exist? In 1955, Alan Newell, Cliff Shaw, and Herbert Simon invented a data structure at Rand Corporation that would quietly power nearly every operating system, database engine, and browser ever written. 70 years later, it is still alive, still running inside the Linux kernel right now on your machine. This is the linked list, and if you think it is obsolete, you have been misled. Today, we are going to look at exactly how linked lists work, what makes them different from arrays at the hardware level, where real production systems rely on them today, and how to know when to use one and when to avoid one. By the end of this, you will have a clear mental model of when to use a linked list, when to use an array, and why the engineers who built Linux, Git, and Redis made the choices they did. You will never confuse a linked list with a legacy artifact again. Every developer eventually hears the same argument. Arrays are always faster, linked lists exist only for interview questions, and nobody actually uses them in real production code. That argument is wrong on all three counts. Linked lists are not a relic. They are a precision tool, one that solves a specific class of problems that arrays simply cannot handle efficiently at scale. The Linux kernel scheduler uses them, Git uses them, your browser uses them, Redis uses them. The glibc memory allocator uses them. These are not toy projects. These are the systems that run the internet. The question is not whether to use linked lists. The question is when. And to answer that question with any precision, you first need to understand what is actually happening in memory when you allocate either structure, because the difference is not just about pointer overhead. When you allocate an array, the runtime asks the operating system for one contiguous block of addresses. Element 0 sits at address 1000, element 1 at 1004, and so on, perfectly sequential in memory. This is called spatial locality, and it is exactly what your CPU cache loves. Modern processors prefetch data in cache lines typically 64 bytes at a time, so reading element 0 almost certainly pulls elements 1 through 15 into the L1 cache for free. Array access patterns are predictable, and predictable patterns let the hardware work ahead of your code. A linked list works completely differently. Each node can live anywhere in heap memory, address 1000, then 2F80, then 1A40. There is no spatial relationship between nodes whatsoever. Every time you follow a pointer to the next node, you jump to a completely different memory location. That is a potential cache miss every single hop. The CPU has no way to predict where you are going next, so it cannot prefetch. This is the fundamental hardware cost of a linked list. You pay in cache efficiency on every traversal. But in exchange, you get something arrays can never give you at any price: true O1 insertion and deletion anywhere in the structure without touching any other element. A linked list is built entirely from nodes. Each node holds exactly two things: a data payload, which can be any type and any size you choose, and one or more pointers connecting it to its neighbors in the list. In a singly linked list, each node has one pointer called next, pointing forward to the following node. The last node's next pointer is set to null, which signals the end of the list. In a doubly linked list, each node carries two pointers, next pointing forward and prev pointing backward. This bidirectional linkage lets you traverse in either direction and delete any node you already have a reference to in O1 time without needing to find its predecessor first, a significant practical advantage. In a circular linked list, the tail node's next pointer loops all the way back to the head, creating a ring structure used in round-robin schedulers, audio ring buffers, and carousel interfaces. The entire entry point into any linked list is a single pointer called head. If head is null, the list is empty. Every traversal, every insert, every delete begins from that one pointer. The structure is minimal by design. Here is what that pointer architecture actually buys you in concrete terms. To insert a new element into the middle of an array at index 2, you must shift every element from index 2 onward one position to the right, then write the new value into the vacated slot. For an array of 1 million elements, inserting at position 0 means moving 1 million elements in memory. Every element has to be touched. That is O of n. Cost grows linearly with the size of the array. Every deletion in the middle has the same problem in reverse. With a linked list, inserting a new node between existing nodes B and D requires exactly two pointer assignments. Set the new node's next pointer to point at D, then update B's next pointer to point at the new node. Two writes, no copying, no shifting. O of 1 constant time, regardless of whether the list contains 10 elements or 10 million. Deletion is equally elegant. Update the predecessor's next pointer to skip over the target node, and it is logically removed from the list. This is the central trade-off made concrete. Arrays are fast to read by index and slow to mutate in the middle. Linked lists are slow to read by index and fast to mutate anywhere you already hold a reference. So when should you actually reach for a linked list in real code? Use one when your workload is write-heavy, frequent inserts and deletes at arbitrary positions where shifting an array would dominate your runtime. Use one when you do not know the required size at allocation time and cannot absorb the cost of repeatedly growing and copying a dynamic array. Use one when you are implementing a queue and need guaranteed O1 in queue at the tail and O1 DQ at the head. Use one for undo and redo systems, where a doubly linked list of state snapshots is the most direct and natural model. Use one for graph adjacency lists representing sparse edge sets, where the number of neighbors per node varies widely. Reach for an array instead when you need random access by index. Linked list index lookup is always O of n, which disqualifies it for lookup-heavy workloads immediately. Choose arrays when cache performance is critical and reads heavily outnumber writes. Choose arrays for binary search for sorting for any algorithm that requires jumping to an arbitrary position. The practical rule is simple. If your access pattern is dominated by reads and random lookups, use an array. If it is dominated by inserts and deletes at arbitrary positions, use a linked list. This is not theoretical. Look at the systems running on your machine right now. The Linux kernel's process scheduler maintains the list of runnable tasks using doubly linked list structures embedded directly inside each process descriptor object. This is how the kernel walks from one process to the next during a context switch. Git stores its commit history as a singly linked list of commit objects, where each commit holds a pointer to its parent, forming the chain you traverse with git log. Your browser's back and forward navigation is a doubly linked list of visited page entries. Pressing back walks the prev pointer, pressing forward walks next. The glibc malloc implementation, which underlies nearly every C and C++ program running on Linux, maintains its free block list as an explicit linked list of memory chunks, threading the list structure through the free memory itself at zero extra cost. MySQL's InnoDB storage engine uses a doubly linked list for its buffer pool LRU eviction policy, deciding which cached pages to flush to disk under memory pressure. Redis exposes a list data type backed by a doubly linked list, giving O1 push and pop at both ends regardless of how long the list grows. Bringing it all together into a clear reference. For random access by index, arrays win decisively, O1 versus ON for linked lists. For cache efficiency on sequential reads, arrays win because of spatial locality and hardware prefetching. For memory overhead per element, arrays win, there is no pointer storage cost. For insert and delete at the head or at any position where you already hold a node reference, linked lists win, O1 versus ON for arrays. For dynamic sizing without paying a reallocation penalty, linked lists win. Every insert is cheap, there is no capacity threshold to cross. For implementing stacks, queues, and dequeues with consistent O1 operations at both ends, linked lists are the natural fit. For sorted data with binary search requirements, arrays are mandatory. For implementation simplicity and readability, arrays win by a clear margin in most languages. The conclusion is not that one is better than the other. It is that they are optimized for completely different access patterns. Knowing which one to reach for in a given situation is one of the clearest signals that separates engineers who understand their tools from those who just know the syntax. Linked lists still exist because no other general-purpose data structure matches their combination of O1 insertion, O1 deletion, and fully dynamic sizing with no reallocation cost. They are not everywhere, but where they belong, nothing else comes close. If this helped clarify something you have been unsure about, consider subscribing. We cover systems concepts like this: memory models, scheduling algorithms, database internals, networking protocols, visualized clearly without the hand waving. New video every week.